So in the first part of this lecture, we learned how to take full adders and connect them with the ripple carry so that I would be propagating the signals from the carry in all the way to the 32 bits or the 64-bit in a 64-bit architecture. And we realized that the time that it would take to propagate the signal was too long for the types of computation that we want to do in modern processors. So one solution to accelerate the computation of the addition is to use something called a carry look-ahead unit. What does the carry look-ahead unit do is to compute two signals, the propagate signal and the generate signal. So the way this is going to work is that I'm going to have a logic to compute each one of those signals in order to accelerate the computation. So what's going to happen is that I'm going to have this unit that is my carry look ahead unit. And what the carry look ahead unit we're going to do is take the carry in bit, and each one of those full adders now will also have a propagate and a generate bit. The propagate bit tells me that if this unit were to receive a carry in, it would propagate that carry in to the output. The generate signal tells me that regardless of the carry in, this unit is generating a carry out. And so I will have then this carry signal that goes to the second unit, which also has a propagate and a generate signal and a sum. And this is the way I connected those circuits with the carry look ahead unit. The advantage of this is that in the end, I have the carry out for that I can propagate to the next unit. And what I'm going to do is to take these propagate signals that I have as input to this carry look ahead, and I will have a propagate and a generate signal for this entire unit of for full adders. So what should be the logic for the propagate and the generate? The propagate is an OR. That dot operator that I have for the the generate is an AND. That dot operator that I have here is the logical operator AND in logic. So this is saying that if both AI and AB are equal 1, then that unit will generate a carry independent of the carry in. So let's say if A2 is 1 and then B2 is 1, I don't need to know the value of the carry in to know that I'm going to be generate a carry out, because regardless of the value of the carry into that unit, I generate a carry out. So this is my generate signal. My propagate signal says that if either AI or BI is equal 1, then if there is a carry in, I'm going to be propagating the carry in. So the only situation where I have both generate and propagate equals 0 is if both of these bits are equal 0. So if they are both equal 0, no matter what the value of the carry in is here, I will not going to have a carry out from this unit. So by doing this, this logic, I can then accelerate the computation of the carry signal that I need for the next units. So how I generate the carry I plus 1 now, the carry I plus 1 will be true if either the generate signal is on. So that means that I have, for example, A2 and B2 equal 1. I don't need to look at the carry in. Or if the propagate signal is on and the carry in is on, right? So if I have a 1 in the carry in and I have a 1 in the propagate, it means that I'm going to be generating the next carry out. So there is a different way that we can look at the idea of carry look ahead. And this way is, and this is actually a common way that we use to reason about logic. So because it can be difficult to visualize electrons moving through wires, we can think about water moving through pipes. So imagine this hydraulic device where my carry in is that jug of water on the top, and either I have water in the jug or I don't have water in that jug. That is my 0 or 1 signal. My generate signal is the water that is in that valve on here. Okay, so if I turn on the generate signal, it means that this water will follow down the pipe and I'm going to see water down here. So if generate is on, I don't need to know whether the propagate will allow that water to come down or not. So now this makes more sense if I put two those in sequence. Now, if I know that this generator here is 1, I don't need to know anything above in the pipe to know that I'm going to have water in the output. Or if I do this way, this is my 4-bit version. Now what happens is that, for example, this generate equal 1 tells me that I'm going to have water out here without me having to wait, for example, for that water to come down. Okay. Now, if this propagate signal is 0 and this generate signal is 0, I know that I don't have water in here because there is no way for water to get there. So here is another example. For example, in this case, in this unit, I have no generate. So all the generates are 0 and all the propagates are closed in this case. So I will not, independent of this carry here, I'm not going to see a carry in here. And here is another situation where I don't have a carry in, but I may have a generator that is turned on. So in this case, I probably going to see this. Actually, this tells me about the generator value. This tells me about the propagate value. So I can analyze. So the P0, that's the propagate for the 4 unit, is given by only the value of the propagate bits, and the G0, that's the generate for the entire ensemble, is giving to me by both the generate and the propagate signal. So this is a way that we can accelerate addition. There has been extensive research in computer architecture. It's called, in a field called computer arithmetics, that is geared towards accelerating arithmetics in computers. The carry look ahead is just one example of how to speed up addition, but we have had more than 40 years of research on how to improve these very basic operations. One of the things that I need to worry about when performing arithmetics in a computer is the possibility that the value that is the result cannot be represented in the number of bits that I have to represent the values. So that situation is called overflow. And here is an illustration of a situation where you end up with overflow. In this illustration, what we have is I'm adding two signed numbers. So the number on the top is +7, the number on the bottom is +1, and I'm doing a representation that is a 2 complement representation. Those are signed numbers. So when I do this addition, 1 + 1 is 0, and there is a carry of 1. 1 + 1 plus 0 is 0, and there is a carry of 1. Again, I have 0 with a carry of 1, and now 1 + 0 + 0 is 1. So the result of my addition is -8. So I add 7 + 1 and I got -8. Obviously, that is not the result that anybody would expect from adding two values in a computer. So we have overflow, and the way we know that we had overflow is the sign of the number has changed. I had two positive numbers and I got a negative result. So if I do an example with 7 + 6, for example, depends on how many bits I have. So if I just add 7 + 6, this is the result that I get. If I represent those two numbers in 32 bits, there is no overflow. So overflow is always related to the number of bits that I have in a representation. So Overflow only happens if the result is out of range. So here's a table that I can look at to know whether I got overflow. If I'm adding two numbers and both numbers are, and one of the numbers is positive, the other number is negative, I cannot get overflow because the margin of the result will be smaller than one of the operands. So there is no overflow if A is negative and B is positive, and there is no overflow if B is negative and A is positive. So if I add two numbers that are of different sign, I cannot get overflow. However, if I add two positive numbers and the result, the sign of the result is 1, which means that the number is negative, it's an indication that I got overflow. I cannot represent the result in my representation. And similarly, if I add two negative numbers and the result is positive, then I got an overflow. So let me stop this part of the lecture here.